Yeah.
So when you live stream, it is automatically recorded, but the recording is not automatically posted. You get a chance to do some editing before it gets posted later on.
Yeah.
I mean, it is recorded, but we can make it private. So, and then we can kind of upload a new version to it.
Okay. Okay.
Yeah.
So inside YouTube itself, there is an editing tool. So
Okay.
you don't even have to download it. Small editing, you can do it in YouTube itself.
We will have to learn more and more of these tools in the next 1 year.
Okay, so now the streaming has started.
Yeah, even here people are slowly joining in, but there's usually a sudden spurt in the last 1 minute.
Mm-hmm.
One minute to go, is that right?
4. Yeah.
4?
It's 4 p.m. here. Yes.
Okay. 4 p.m. And in Portugal, it's 3, is it?
Yes, it's 1 less.
Okay. Okay. Yeah, Spain is also on the. Okay, so maybe Sunil, you can tell me when I should start.
Yeah, maybe 1 more minute. Yeah, I guess we can
Okay,
start. Right?
yeah. Okay. So, hello everybody. Welcome back to FSTTCS, and welcome to this session with the fourth invited talk of the conference. It's my privilege to introduce the speaker today, Albert Atserias, who is at the University Politècnica Catalunya in Barcelona in Spain. A little bit about Albert. So he did his bachelor's study at Barcelona, and then somehow, and then he did his master's at Santa Cruz and did his PhD in both places. And since then, he's been, I think more or less since then, he's been at Barcelona, at Catalunya. His research interests are computational complexity, combinatorics, logic, and he's made many very fundamental, deep contributions to proof complexity. In particular, one of the things which he did very early on in his PhD days and soon after was to adapt a technique which is bread and butter in finite model theory, the Ehrenfreise games. So he took one version of those games, which is used to prove inexpressibility in FMT, and used it to devise a technique for size lower bounds and space lower bounds and proof complexity. This was, I mean, really path-breaking work. Like I said, he's made many, many contributions subsequently. So he also used these games to applied them to lift and project methods in mathematical programming and optimization. He has worked on algebraic proof systems. He's worked on he has done some very nice work on circularity and soundness and proofs in symmetries and isomorphism. And one of the questions that he has been interested in right from his PhD days is this notion of proof search and what can be said about it. And very recently, last year, the best paper at Fox 2019 went to work which he did, which more or less resolved a long-standing open question here. So now he's going to share with us some of his insights about these proofs of soundness and proof search. I'm really looking forward to your talk, Albert. Over to you.
Thank you very much, Mina. Thank you for this kind introduction, and also thank you for the invitation to the conference. Of course, I would have loved to be in India. It would have been my first time, but too bad I couldn't do it this time. So hopefully next time. All right, so I'm going to talk about proofs of soundness and proof search indeed. And let me start with two giants of the 20th century. So here is Gödel and von Neumann. And it's a well-known story that in 1956, Gödel wrote a letter to von Neumann. And this letter was talking about a topic that we would today call proof complexity. So let's read what Gödel was saying in this letter. So he was saying the following: one can obviously easily construct a Turing machine which for every formula f in first order predicate logic and every natural number n allows one to decide if there is a proof of f of length n, where the length is the number of symbols. Let psi be the number of steps the machine requires to do this, and let phi of n be the maximum of psi over all formulas. The question is how fast phi of n grows for an optimal machine. One can show that it's at least linear. If there were really a machine with linear phi of n, this would have consequences of the greatest importance. So here Gödel was interested in the proof search problem, really. And proof search, the way we formulate it is the following. We're given a tautology and we want to find the proof. And the tautology comes from some language with certain semantics. And the proof depends on the proof system on which you want to find this proof. And that is what we call the syntax for tautologies. So, and more generally, we can formulate this in these modern terms of computational complexity when we're talking about abstract proof systems, where we're given an X from some set A, and we want to find a Y, which is a witness for a verifier, PXY, which is a polynomial time decidable verifier. And notice here that I'm not insisting on the proof to have polynomial length. So I'm just saying it's just a witness that some polynomial time verifiable condition holds. Now let me give three examples. So the first example is, of course, the NP search problems that are in fact NP hard. Like, for example, you're given a three colorable graph and you want to find the three coloring. That's an example of a proof system. But there is another proof system for the same thing. And here is a little bit convoluted one. It says that you're given a three colorable graph and you want to find the proof of its three colorability in some formal system. Well, it's a bit convoluted, but the reason it is convoluted is because these are, although they are the same theorems, and so the same statements, and different proof systems, as a proof search problem, these are equivalent problems. And this follows from the fact that they are NP complete, and because you have Levin reductions one way to the other. So the second example instead is an example where you have NP search problems that are not as hard as NP hard, and where the proof system makes a big difference. So consider factoring, for example, or you're given a composite number and you want to find a non-trivial factor. Of course, a non-trivial factor is a proof of the compositeness of a number. But you could also think of a proof of compositeness to be, for example, a Miller-Rabin witness, where the Miller-Rabin witness is what you find by the probabilistic polynomial time algorithm. And that, of course, can be solved. The proof search corresponding to this proof system can be solved in probabilistic polynomial time. While the non-trivial factor for composite, the best that is known so far, is quantum polynomial time. But in this particular example, if you want to decide compositeness or the same as primality, which is the complement, then of course you can also find an AKS witness, AKS standing for Agrawal, Kayal, and Saxera. And of course, this you can do in polynomial time. And these three proof systems, therefore, for the same problem, give different search problems. And the third example is where we're looking at problems that are well beyond NP search. And this is the example where the witnesses are not necessarily polynomially bounded. So the first example is where you're given a tautology of predicate logic. That's exactly what Gödel was talking about. And you want to find a proof in predicate calculus. And in this case, not only the proof is not polynomially bounded, but it's not even computably bounded. But in computational complexity, what we care more is about propositional logic, because in this case, the proofs in propositional calculus, you can find them to be at most exponentially big. Of course, different proof systems give, again, different search problems. And then, so now back to a little bit of history. In 1971, there's, of course, Cook's paper where he proved that SAT is NP complete. But if you look at the title, and everybody knows the title, it's the complexity of theorem proving procedures. So really what Steve Cook was talking about is he introduced here what is later came to be known as Cook's program. So Cook's program was really proof complexity. And so the very last sentence in the abstract or summary is the following. It says, a method of measuring the complexity of proof procedures for the predicate calculus is introduced and discussed. And then if you go at the end of the paper, then he goes ahead and says that the field of mechanical theorem proving badly needs a basis for comparing and evaluating the dozens of procedures which appear in the literature. Performance of a procedure on examples by computer is a good criterion, but not sufficient, unless the procedure proves useful in some practical way. A theoretical complexity criterion is needed, which will bring out fundamental limitations and suggests new ideas, I think he says. So in fact, Cook himself pursued this program, and it later was caught up by many people. So this is what's known as Cook program. And together with Rekov, and this was his thesis, they introduced this notion of P simulation. So they say that a proof system Q P simulates another proof system P if there is a polynomial time computable function that takes proofs in P and maps them to proofs in Q. So this way we say that Q simulates P, or P simulates because it's polynomial time computable. And this notion of comparison between proof systems, which is what Cook was asking in his paper, it's the kickoff of what we know today as proof complexity. Proof complexity developed enormously, but what came out of the Cook-Rekov paper itself was that what is really important about the proof system is not so much the inference rules that you use if you're looking at deductive proof systems, but the complexity of the lines in the proof. So we're talking about deductive proof systems where you have some axioms and then you derive some consequences of these axioms. And these lines in the proof, you write them in some way as Boolean functions. And the way you write these lines is what determines the complexity of the proofs, not so much the inference rules. So that's why people looked at this hierarchy of proof systems inspired from the hierarchy of complexity classes. So resolution is a very important proof system that we'll be talking about a lot. And this is based on clauses. So these are disjunctions of literals. And then above resolution, we have stronger proof systems where instead of clauses, we're talking with KDNFs or AC0 Frege, that would be bounded depth formulas. TC0 Frege would have threshold formulas of bounded depth. And then Frege and extended Frege, these are formulas and circuits. Of course, you can go even farther up with more complicated stuff. But what about below? That's also an important refinement. So there are refinements of resolution, for example, regular resolution and tree-like resolution. So in regular, what we ask is that the proof graph, that is the graph of inferences that you make up the proof, you want it to be read once in some well-defined sense. While in tree-like, that's even more clear, you want the proof graph to be a tree. So that's a special shape. In general resolution, the proof graph doesn't have to be a tree. It has to be acyclic by the definition, but it doesn't have to be a tree. All right, so this hierarchy of proof system was studied for many years. And so let me give you the rule of resolution, just that we're on the same page. So if you have C or X and D or not X, then of course you can infer C or D. And these are called the resolvent, the left premise and the right premise. So this is the basic rule of inference. You can use this for all proof systems by changing the literals by formulas in general. All right, so there were a couple of themes that were studied in proof complexity. So then I will highlight two themes, and there are many others that have been studied, but two themes were very important. One is lower bounds. So lower bounds means trying to show that these proof systems always have hard formulas, meaning that their shortest proofs must be exponentially big, or at least super polynomially big. And this was already asked in Cook's paper in 1971 about resolution. And he said that he didn't know hard examples for even for Davis-Putnam, he was not aware. And then this theorem of Haken, 15 years later, proved what Cook was asking for. So he proved that resolution must have exponentially long proofs of. So every proof of the pigeonhole principle must be exponentially big. The pigeonhole principle is a natural conjunctive normal form, a formula that states that X codes a one-to-one map from a large set into a small set, n plus 1 pigeons and n holes. And of course, this is not satisfiable. This is a contradiction. But proving that this is a contradiction requires size exponential in the number of pigeons. All right, so this is theme one, lower bounds. And from here, there are many, many good results in proof complexity, starting with Haken. The second theme that I want to highlight is that of proof search and automatability. And this was started also early enough, but the results didn't come out as early. So here, the question we're asking for is, given an unsatisfiable CNF formula, you want to find a resolution refutation or a refutation in whatever proof system you want, but we'll focus on resolution for now. Another question is you want to estimate the resolution proof length of F, so meaning proof length, meaning the shortest proof. And I put it a bit vague, like estimate, because maybe what we want is to approximate. We don't want to compute the exact, etc., etc. You can imagine different variants of the problem. All right, so this was 1971, the start of Cook's program. And now let's fast forward 30 years and see what happened. And something interesting happened and surprising, which was the SAT solver revolution, as it's called. And this started, people put it in the early 2000s, 2001 to be more precise. So it so happened that people started writing programs that were implementing search procedures for satisfiability, for searching for satisfying assignments or proofs of unsatisfiability. And it so happens today that SAT solvers routinely find such things for formulas of many, many variables and thousands of variables. And you can imagine that if you have thousands of variables, the search space of satisfying assignments is ridiculously big. But if 2 to the 1000 is big, then the search space of proofs is even bigger. I mean, it's doubly exponential. So even though routinely you throw them a formula that comes from some application domain, and the SAT solver is likely to find this satisfying assignment or a proof of unsatisfiability. There's a spectacular example, and this didn't come from an application domain exactly, except, well, if you want to call mathematics an application domain, then fine. It's an application to mathematics. So this was called the 200 terabyte math proof is largest ever. And this was the headline in the Nature article. So it was proved that, so it solved the conjecture in Ramsey theory. So the conjecture, it says the following. So if you take numbers from 1 to 7,825, then you cannot partition them into two parts, each part without Pythagorean triples. And a Pythagorean triple is a triple of, so these are numbers, so a squared plus b squared equals to c squared. So you cannot partition this thing, while if you do it with 7,824, then you can partition it. So here we have an example of a satisfiable instance, the small one, 7,824. So you have a satisfying assignment is the partition. And when you go one beyond, then it's no longer satisfiable. And the number of variables of this formula, if you write it just naively, it's precisely this, 7,824 variables. Yes, and this is how they wrote it initially, and then they applied all sorts of optimizations to try to reduce the set of variables to 5,000 first, and then even further. And in the end, what they found is the solution and the proof of unsatisfiability for 7,825. So this is a solution for 7,824. The white means that it's either blue or red, it doesn't matter. And if you go one more, then it doesn't exist, and it's provable, and it produces a resolution proof, or a proof of some sort. So this was a spectacular success of SAT solvers for a huge number of variables. So what's happening here? Might it be that SAT solvers solve the proof search problem for resolution, or what's happening? So let's try to understand. So we went to 2000s. Now around that time, there were also some positive automatability results. So what is automatability? I need to define this. So here's the definition. So we're looking at this proof search variant. So you want to find approximately small p proofs in polynomial time under the promise that small proofs exist. So the point of this statement is that, well, if small proofs don't exist, then why looking for them? You cannot even read them, right? So if it's exponentially big proof, then you don't have time to find them. What you really want is that when there is a small proof, you want to find that one. And on top of it, you don't, well, maybe not that one exactly, but something that is approximately of that size. Another variant of this, and this is the original definition, is that if you want to find proofs in time polynomial, not in the formula, but in the size of the smallest proof. So you put the size of the smallest proof as a benchmark, and that's what you need to go for. And in that case, we say that the proof system P is automatable in polynomial time. All right, so this is the definition. I hope it's clear what the definition is. You want to find proofs in time polynomial in the smallest proof. Of course, you have no idea what the smallest proof is. And that's part of the game. Okay, so there were some positive results that were quite spectacular. And here is the one. So Beam and Pitasi proved that the tree-like resolution, so this is the version of resolution where the proof graph is restricted to be a tree, is automatable in time n to the log s, where n is the number of variables and s is the smallest tree-like refutation. So here we're allowing not polynomial time, but a little bit more. In fact, this is quasi-polynomial time in the size of the smallest proof. So this is a partial automatability result, or automatability in quasi-polynomial time. So in fact, the ideas here were extremely influential for proof complexity. So for one thing, the ideas here were influential for what later came to be known as the Benson-Wigderson theorem, which is not this one. I mean, the theorem is a theorem about width and size. But the consequence of that theorem is the fact that you have an automatability algorithm for resolution without any restriction, which runs in this subexponential function. So again, S is the number of, N is the number of variables, and here S is the size of the smallest resolution proof, general resolution proof. And K is the width of the initial clauses. This is a technicality because you can always reduce to 3 SAT without any problem. So K equals 3 is fine. I want you to notice what is the nature of this function. So it's sub-exponential in some sense. So for example, if S is polynomial, then this is polylogarithmic or even logarithmic. So this is n times log, so square root of n times log, and then you have this n, which if you put in the exponent, it gives you this running time here. So exponential in the square root of n with some polylog factors in there. So exponential in the square root of the number of variables is, of course, very non-trivial. So it has to be compared with ETH, because ETH states that such a thing cannot be done. But of course, the assumption is that there is a proof of polynomial size. So only in that case, you're guaranteed to run in sub-exponential time. For example, what happens if the proof is exponentially big, like in Pigeon-Hole principle? So if it's exponentially big, then log 2 to the n is just n. So you get n squared. So you get square root of n squared, that's n. So that's n to the n, which is even worse than exponential. Okay. So, but I insist, what you want here is you want to find short proofs. So if you have a short proof, can you do better than exhaustive search? The answer is yes. Okay. So this it's a fantastic thing to be giving an invited talk, because then I can talk about the proof of Bimpitasi, because I find it very beautiful. It's simple and beautiful. So here is what the Bimpitasi algorithm is. Remember, this is for tree-like resolution, and we're trying to search for a proof in tree resolution that is as small as possible. Ideally, the smallest possible, but that will not be possible in general. Okay, so first an observation. Suppose you have this tree-like resolution proof, or refutation it should be called. Then if you flip over, then and you interpret the last resolution step. So this is a resolution step. From xi and not xi, you derive the empty clause, right? The last resolution step, you can interpret it as a query. And then this query is when it's 0, you go left, and when it's 1, you go right. And what you're interpreting this is as a query for saying which one of the two is falsified. And then when it's falsified, you can proceed recursively to the subtree. So this is a search, this is a decision tree that what will it do? Well, if you continue through the clause that is always falsified by the assignment, then eventually you will reach an initial clause like CI, which is falsified. So this decision tree is a decision tree for the falsified clause search problem. So you're searching for a clause that is falsified by the assignment. Good. So this is only reformulating the notion of decision of resolution proof, tree-like resolution proof. And now what we are asked to is to find the smallest decision tree, or something close to the smallest decision tree, for the falsified clause problem. And here's the algorithm. So I'm going to state it non-deterministically, and then we can remove the non-determinism. So we're given the function f and the size s, and you have the guarantee that there is a tree-like resolution refutation of size less than s. Well, if you don't know s, that's okay. You can always do doubling until you find the one that works. Okay, so let's assume you know s. And now what you do is you guess the variable that goes in the root. You guess which side. This is the bit b. And then you recurse on the restriction of the formula with this variable set to b and with s set to 1/2 of s. So basically what you're trying to do is you're searching for this small subtree, which always exists, right? And once you find, so you guess these guys and you recurse, and if this guess succeeds to find a tree, then you recurse on the other one with a full s. So here you could say, maybe I could use s minus 1, but no, let's use full s. And the reason for that is that we don't know if the guess that worked in the non-determinism is the one for the right x. We just don't know that. But what we know is that because there is a full tree, then any restriction is going to be a tree of smaller size. So for this tree, for this restriction, you still have size s. And therefore, this you're guaranteed to succeed. So the algorithm is correct. It's a little subtle. And so what is the running time? Well, first of all, we need to get rid of this non-determinism, but that we do by some sort of exhaustive search. So you have a number of choices in the guess, so 2n, because you have n variables and two polarities. And then this is the recursive call that you're exhausting, right? But once you find this one that succeeds, then the other side, you only run it once. That's the point. And then in addition to this running time, there is some overhead for manipulating the formula. So if you solve this recurrence, it gives you the n to the log s that we were talking about. It's a beautiful algorithm, and so I think it really deserves to be known. It gives you quasi-polynomial time automatability for tree-like resolution. All right, so the next concept I want to talk about is feasible interpolation. This is an important concept, and this is way towards proofs of soundness, which is the main topic of the talk, right? So there's this concept from logic, which is called Craig interpolants, but it's from logic, but it's also from circuit complexity, as you will see. So suppose that you have a conjunction where you have some common variables. X appears both in F and in G. These are formulas. And Y and Z are own variables. So Y only appears in F. This is a sequence of variables, by the way. And Z only appears in G. And let's suppose this contradiction, this conjunction is a contradiction. Well, then there's a Craig interpolant, as it's called, which is a formula that only takes the common variables and determines which of the two is unsatisfiable. F or G, one of the two must be, because the conjunction is unsatisfiable. So for every fixed value of X, every fixed assignment of X, either F or G must be unsatisfiable. Otherwise, you would plug the satisfying assignments and then the whole thing would be satisfied, right? So the interpolant tells you which one is a contradiction for fixed X. So let me give you 3 examples of interpolants. So one is in graph theory, and this is a quite important example, where suppose the clique is the formula that says that Y codes a k+1 clique of the graph X. Let's say that X codes a graph. So this is, of course, just the proof system for k cliques, or k+1 cliques. Now, the colorability formula says that Z codes a proper k-coloring of X. And again, this is just a straightforward way of writing this formula. Now, of course, this is unsatisfiable because you cannot have at the same time a k+1 clique and a k-coloring. So you have a contradiction here, and that's the kind of things that we want. By the way, here we're using pigeonhole implicitly because you have k+1 things that you need to color with k colors. Right? All right. Okay, so this is an example, and then the question is, what are the interpolants? Well, this is the conjunction. So Y is a k+1 clique and Z is a k coloring. So the interpolant is going to tell us that either the left one is unsatisfiable, and then the clique number is at most k, or the right hand side is unsatisfiable, and then the chromatic number is more than k. So the interpolant is telling apart these two things. And an example of an interpolant that is very famous is log theta. So log theta compared to k is going to be an interpolant of this type. On top of it, it's a polynomial time computable interpolant. But this is only an example that I'm putting. So let's go to the second example of interpolation. And interpolants are also relevant for cryptography. So suppose we have a permutation that is easy to compute, but it's hard to invert. It doesn't have to be, let's say, hard in the worst case. We don't need average case hardness here. And now let's look at these formulas. These formulas say that Y is a preimage of X, so f of Y is X, and the ith bit is 1. And the other formula says that the preimage of X, Z, has ith bit equal to 0. Now, of course, because this is a permutation, if Y and Z are both preimages of X, then they are equal. So the conjunction is a contradiction because f is 1 to 1. It's a permutation, in particular, it's 1 to 1. So what are the interpolants of this thing? So this is the conjunction, and the interpolant is going to tell us that either the left one is unsatisfiable or the right side one is unsatisfiable, and which one is going to tell us which bit is the ith one of the preimage. The preimage is uniquely defined. So any interpolant is going to invert the function that is supposedly is hard to invert. Okay, the third example will come out later, which is going to be actually proofs of soundness. So this motivated this question of feasible interpolation, and Jan Krajicek introduced this in proof complexity. And the feasible interpolation property of a proof system says that whenever you have a contradiction like this, of this form, F and G, then you can always find interpolants of circuit size polynomial in the size of their P refutations, the refutations in the proof system. Of course, notice that I'm saying size polynomial in the refutation, and the refutation might be much bigger than the formula itself. But the point is what happens if you have small proofs. That's an interesting case. So Krajicek himself introduced this concept and then actually proved that some proof system has interpolation. One of them is resolution. So resolution has feasible interpolation, and even more, it has monotone feasible interpolation. Monotone means that the interpolating circuit is in fact monotone when the formulas have some syntactic property that allows them to be monotone. So in particular, one consequence of this result that you have monotone interpolation for resolution is that the clique and coloring formulas, which interpolate, well, whose interpolants are supposed to separate chromatic number and clique number, well, they cannot have small proofs in resolution, because if they had small proofs in resolution, then by monotone interpolation, they would have small monotone circuits. But we know that small monotone circuits for these interpolants do not exist. And this is the seminal results of Razborov on circuit lower bounds for monotone functions. I mean, monotone circuit lower bounds for monotone functions. So this was a beautiful application of circuit complexity to proof complexity. So it gave lower bounds for certain formulas. So now we go to the topic of here. Let's relate these two concepts. So on one hand, we have interpolation, and we introduce automatability. So how are these two things connected? So they are connected in one direction. This is quite clear, and this was observed by the people who introduced the concept of automatability. And one of the motivations for introducing it was this lemma, which says that if you have a proof system that is automatable, then it has feasible interpolation. So the argument fits in this slide. In fact, this is the slide. So what do we want to do? We want to show that, so let's assume that the proof system is automatable, and we want to find an interpolant for this thing, assuming that you have a proof of size S. So you have a small proof of size S, and we want to find an interpolant of size polynomial in S. And here it is. So what does it say? Well, the interpolant, what it says is that if you apply the automating algorithm on G, restricted to the input X, X0, if you apply the automating algorithm, then you find refutation of G, and this is the verifier for this fact. So this verifier, this is a polynomial time verifier that checks that the right-hand side, so A, is the refutation of the left-hand side. And these are just the formulas coded. That's why I put these brackets, because you put the formulas, syntactically the formulas are plugged into this. So why does this work? Well, let's see. So first of all, if the interpolant is yes, so if this evaluates to yes, then it means that indeed the algorithm found a refutation. And if it found a refutation of G, then it means that G is unsatisfiable. And that's what you want from the interpolant. On the other hand, what happens if the interpolant doesn't find such a thing? Well, if it doesn't, meaning the answer is no, right? So if it doesn't, it means that A doesn't find a refutation. But if it doesn't find a refutation in time P of S, then it means that this formula was not unsatisfiable in the first place. Sorry, that it didn't have a small proof in the first place. Yes, it didn't have a small proof in the first place. But from the assumption that the conjunction has a small proof, it would follow, if F were satisfiable, that you could restrict this proof and get a small proof of G. So let me repeat. So suppose you have a small proof of the conjunction, and suppose F were satisfiable. Well, then you plug the satisfying assignment for F, and you would get a small proof of G, just by restricting the proof of the big conjunction. Once you have a small proof of G, A finds it. And once A finds it, then interpolant is yes. So this is the argument for the existence of interpolation. I mean, it's as clean as one slide. Maybe I didn't explain so well, but believe me, it's very clean. All right, so this is the connection between automatability and interpolation. So one consequence of this is that Krajicek and Pudlak went ahead and used this to show that certain proof systems don't have feasible interpolation under an assumption, a cryptographic assumption. For extended Frege does not have feasible interpolation unless the RSA proof system is broken by polynomial size circuits. And this extended Frege, if you remember from the hierarchy of proof systems, is the one that appears at the top. So these are circuits, you're reasoning with circuits. So why does it follow from what we have so far? Well, it follows after they prove the following. So they need to prove that the interpolation statement for RSA, the cryptographic system, has polynomial size extended Frege refutations, so EF. So this is an unsatisfiable formula because RSA is a permutation once you're given the key. And it's a kind of contradiction from one-way functions that we discussed earlier. So what they proved, Krajicek and Pudlak proved, is that this has small refutations in extended Frege. So the consequence then is that you don't have feasible interpolation because you would break RSA. And a corollary, of course, then is that because if a proof system is automatable, then it has feasible interpolation, and it follows that extended Frege is not automatable unless you could break RSA by polynomial size circuits. In fact, even polynomial time. All right, so this is the first non-automatability result that was proved. So this is saying that the proof search for extended Frege cannot be solved efficiently, even if you are happy with approximation. And this was later improved to other proof systems, a bit weaker in the hierarchy, like Frege or TC0 Frege and even AC0 Frege. But AC0 Frege required, instead of polynomial time here, you required here subexponential time. For the other ones, it was fine. Polynomial time is fine. All right, so we have non-automatability of certain relatively strong proof systems. That's not that unsurprising, but it's good that we have actually proofs of this, or at least conditional proofs. And now we come to the topic of soundness proofs and automatability. So what are the soundness proofs, and how do they what do they have to do with proof search? So it's again about interpolation. And this is the third example of interpolation that you can improve complexity. And in this case, it's improved complexity. The other case were cryptography and graph theory. So here we are talking about the following question. So let's say SAT is the verifier for satisfying assignments. So Y codes a satisfying assignment of X. This is extremely straightforward formula. You can write as a CNF. And then let's say that you're also writing that Z codes a P refutation of X, and you write this as a CNF, maybe because you have auxiliary variables that help you to express things in CNF. And all these variables you can plug into Z, and then you have a CNF that expresses that Z codes a P refutation of X. And let's parameterize these formulas by the proof system and by the size of the proof, size meaning the length. And now, of course, this is a contradiction. You cannot have a satisfying assignment and at the same time as a refutation. Right? The refutation is a proof of unsatisfiability, so you cannot have both things. And that's because the proof system, you're assuming that it's sound. So it's a contradiction of the type that we want. And now what we have to ask is, what are the interpolants of such a statement? So let's interpret them. So the interpolants are, well, an interpolant is a formula or a Boolean function that tells you which of the two is unsatisfiable for fixed X. So if the interpolant is 0, then the one that is unsatisfiable is the formula that says that X is satisfiable. And if the interpolant gives you 1, then the one that is unsatisfiable is the one that says that there is a refutation. So if you think of this, this is sort of a dual of what a SAT solver does. So remember, a SAT solver, what it does is you're given a CNF and it finds satisfying assignments or refutations. Yes? And what the interpolant is doing is saying, well, for this guy, either it's unsatisfiable, or it doesn't have short proofs. It's a kind of a dual. If you write the contrapositive, which is very straightforward, then what it says is that when the formula is satisfiable, then the interpolant predicts this, but only in case you're guaranteed that if it had not been satisfiable, it would have a small proof. Okay, this is a kind of an interpretation of what the interpolant says. All right, so in some sense, it is related to proof search because it is related to this problem that the set solver is solving. But there is a better connection. So for example, one thing is that if the proof search problem for P were solvable efficiently in polynomial time, if it were automatable, then you would have a polynomial time interpolant for the SAT and REF formula. So let's discuss it. So let's assume that P is automatable, and I claim that this thing here is an interpolant for the soundness statement. So A is the automating algorithm, and P is the running time of the automating algorithm. And now I want to argue that if the interpolant holds, then the right-hand side is unsatisfiable. But that's clear, right? Because, well, if it were satisfiable, then X would have a short proof. And if it had a short proof, then the automating algorithm would find it. Yeah, and then this cannot be false. So indeed, if the interpolant is true, then the right-hand side is unsatisfiable. And now let's argue that if the interpolant is false, then the left-hand side is unsatisfiable. Well, let's see, if it's false, it means that the algorithm found a refutation, yes? But if it found a refutation, then it cannot be satisfiable because it's sound. So indeed, this is an interpolant. So if you have an automating algorithm for the proof system, then you have an interpolant of polynomial size. If you stare a little bit to this for a couple of seconds, you realize that you can do a little bit more by allowing a little bit less, by assuming a little bit less. So instead of B being automatable, let's say that not P, but maybe some proof system that simulates P is automatable. So let's say Q, P simulates P, it's a stronger proof system, and it's this one that is automatable. Then I claim that this is still an interpolant. The difference here is that now A is the automating algorithm for Q, and the polynomial that I'm plugging here is no longer the running time of the algorithm alone, but it's the composition of the running time with the polynomial that gives you the simulation. So if you stare for 2 seconds on this formula, you will see that the same argument that I gave before works for this one. So what have we shown then? We have shown that you have some interpolants for the soundness statement of polynomial time if you could automate P or automate something stronger. So this is what Putlak stated in this theorem, and he actually proved the reverse. So this is a characterization. So when do the soundness statements have polynomial time interpolants? Question. So when is it the case for a proof system P that its soundness can be interpolated in polynomial time? Well, this happens precisely when there is an automatable proof system that simulates P. So this concept that Putlak came up with, he didn't give it a name, and in this paper with Bonnet, we gave it a name. We called it weakly automatable, and this is what is now called P is weakly automatable in terms of Q. All right. Now, P would be weakly automatable if it were automatable in terms of some other proof system. Good, so this is the connection between proof search and soundness proofs. So it raises an automatic question now. So remember, let me go back to this. So we want to automate P, but okay, maybe what we can do is automate some proof system that simulates P. That's kind of good enough, I think, for proof search. So all it suffices is to find polynomial time interpolants or polynomial size circuits. Actually, it doesn't matter. It's not so important, I mean, for the soundness of the proof system P. So, and remember, resolution has feasible interpolation. So the question this raises is, does the soundness of resolution have short proofs in resolution? So we looked at this and unfortunately no, but it requires some proof. So we need to show that resolution proofs of its own soundness, meaning the SAT and REF formula, must be of super polynomial size. But on the other hand, we had some positive results. We argued that this is kind of optimal because you have polynomial size soundness proofs in a slightly stronger proof system, which is the proof system in the hierarchy, the one that goes just above resolution. This is 2DNF. Instead of clauses, you have 2DNFs in your reasoning power. So if you allow 2DNFs, then you can prove the soundness of resolution. So here there is a lower bound for resolution itself and an upper bound for res2. The lower bound, by the way, was by reduction from the clique and coloring formulas that we discussed earlier. And the proof is kind of straightforward. Just formulate the right thing and just follow the definitions. But it's a good observation. So and of course it raises the question now, what happens with the res2? Does it have feasible interpolation? And this is open. It's open whether it has feasible interpolation. All right, so this was a journey through the topics of proof complexity. So remember, we had these two themes. One was lower bounds, and the other theme was proof search. And we were focusing on proof search, but notice that along the way to proof search, all the results about lower bounds were relevant, right? So the two things are actually going one hand by hand with the other. And in fact, the Beam-Pitasi algorithm that gives you a quasi-polynomial time automating algorithm for tree-like resolution, the methods of that algorithm were later used to prove lower bounds. So this is the width method of Benzes and Peterson. So in fact, the two things are very, very, very related. Okay, so we had that automating extended Frege is as hard as cryptography. So what about resolution? Well, there were some results, and an important result in 2001, as early as 2001, was this result of Alekhnovich and Razborov, which said that, well, resolution is not automatable. Even though it has feasible interpolation, it is not automatable unless some assumption in parameterized complexity fails. So at the time, this was a tour de force. It was a difficult and complicated proof, and using many tools. It's still hard to understand. It's a very powerful methods that it's using. And it's a strong result in the sense that it's ruling out automating algorithms under this widely believed assumption. The assumption is still quite strong, and in a certain sense is not optimal, because well, if WP happens to be tractable, then there's no reason why resolution would be automatable. So, so it's not an if and only if. It's not. Another sort of weakness of the result is that the best lower bound it gives is quasi-polynomial. So it's not automatable in polynomial time. So what time does it require? Well, the result says that, or the method can only give lower bounds of type n to the log n if the size of the proof is polynomial. And this is even assuming a stronger assumption, which is the exponential time hypothesis. This was only realized recently. And there is a reason why the lower bound is only quasi-polynomial, and it's even weaker than the usual quasi-polynomials. But it cannot be more than quasi-polynomial because this result applies even to tree-like resolution, which we know is quasi-polynomial time automatable. So there was a reason, and therefore it means that if we want to show that resolution is not automatable in sub-exponential time, say, then we cannot apply this method because it would apply to tree-like resolution. That's not true. Okay, so after a long journey, so this was 2001, after a long journey, last year with Moritz Müller, we managed to prove that an optimal non-automatability result for resolution So resolution is not automatable in polynomial time unless P equals NP. And the same proof shows that it's not automatable in sub-exponential time unless the exponential time hypothesis fails. So in fact, this P equals NP is an optimal assumption, because if P equals NP, then of course you can automate things. You can solve proof search, you can solve anything you want. So it's an optimal assumption. Most importantly, I believe that it introduces a new method. And the nice thing for this talk is that it's based on soundness proofs. So I'm going to give a glimpse at the proof. I have a couple of minutes left, or more, not so much more. So let me give you a glimpse at the proof. So you want to show that proof search is NP hard, yes? Proof search is NP hard. So we want to reduce the satisfiability problem for general formulas. So you're given a formula F, and you want to map it to some other formula in such a way that, well, if F is satisfiable, then you want this new formula G to have small refutations in resolution. You want it to be unsatisfiable and have small refutations. In the case that F is unsatisfiable, then you want this new formula to not have small refutations. So you want to have this, so this means that if you were able to automate resolution proofs, then you would be able to distinguish these two cases, right, in polynomial time, even sub-exponential time, and then you would be able to tell apart satisfiable from unsatisfiable for an arbitrary formula, and that's the NP hardness. Okay, so how do we do this construction? So here's the spoiler alert, if you want to read the paper. So we take as our formula G, this is the formula that we construct from F. Given F, we construct G. We take it to be the ref from sat and ref. Remember the soundness statement? Satisfiable or refutable. So we take it to be ref, except that it's a small variant. So we need to take it R ref. It's a relativized ref, but it's really a small variant. Everything else goes through. Then the upper bound, we proved it in the same way by using the soundness proof on resolution in res2. This was necessary. This was useful. And the lower bound required an adversary argument of the kind of that we do in proof complexity very often. But it required, it was a little tricky, but we managed to do it. So this solved, this is all I want to say about this proof. It used the soundness statements, but it was not so nice that we couldn't use exactly the same statement of soundness. It was nice that Michal Garlik, a few months after our results, managed to remove this R. So the choice where you use the real refutation statement also works. So he managed to, this was conjectured in our paper and Garlik solved it. A nice corollary of this is that now it follows from this that resolution proves of its own soundness. Remember, we had a super polynomial lower bound. It now follows that they must be exponentially big. So I think this completely closes the question of what is the soundness proof for resolution, the soundness proof complexity. And if I have 1 or 2 more minutes, I think I do.
Yeah,
right?
sure. Yeah.
So let me discuss this proof because it uses lots of things and it's very simple. Simple when you put together the proof of the corollary, not the proof of the theorem. The proof of the theorem is the proof of Garlik's theorem, where you can use this, is sophisticated. That's why we didn't find it. But the corollary is very nice, and simple. So here it is. So we want to show that this requires exponential size refutations, the soundness statement. So suppose it has sub-exponential, so it requires exponential size. So suppose it has sub-exponential proofs, the refutation. Now use as X an arbitrary unsatisfiable formula and plug it in. Now by the theorem, it says that this, because F is unsatisfiable, we are in the second case of the theorem, right? It says the second says that if F is unsatisfiable, then the refutation statement of it is hard. So the refutation statement for F that says that F has a small refutation is hard. That's why the theorem. Now, by interpolation, it follows, because this, we're assuming it has a small proof, sub-exponentially small proof, and it follows that because the right-hand side is hard, then the left-hand side must be easy. This is by a small variant of the interpolation theorem, and this is the case. But then, if this statement that says that SAT is, so the statement says that F is satisfiable, and you have a small refutation of this, so it follows that F is unsatisfiable because you have a refutation of its satisfiability. And from this refutation, you can extract the refutation of F itself. So F itself is sub-exponentially easy. But F was arbitrary. So we could have taken as F my pigeonhole principle, right? And pigeonhole principle is hard, it's exponentially hard. So you get the contradiction and the proof is over. Okay, to wrap up one slide. So here's a timeline of what happened in the proof search problem since the SAT solving revolution. So in 2001, there was this chaff implementation where it started giving all sorts of success in finding satisfying assignments of proofs of unsatisfiability. So it was kind of the first evidence that this problem is, proof search is easy, maybe. Remember, the search space of satisfying assignments is big, but the search space of proofs is even bigger. So it was kind of amazing that they were finding it. At the same time, Alekhnovich and Razborov gave evidence that the problem must be hard, but only some weak evidence in some sense that it's quasi-polynomial and only under an assumption that is not so well established. So 15 years later came this Pythagorean triples problem that we talked about, where it found an amazing proof, 2000 terabyte size proof. And so it looked like, again, search seems to be doable. But today, in 2020, almost 2021, today we know that proof search is as hard as it can be. So it's now, there's no other option here. I mean, it's just endly hard. So this puts a challenge to the SAT solving community, which is, okay, so plug these formulas. After all, these formulas are, they are not that inexpensive, so you can code them. So would that give you better proof search space, or I don't know. These are questions to be investigated in some other occasion. So now I'll finish here, and thank you very much for your attention.
Thank you very much, Albert. That was a really beautiful talk. So yeah, so open now to questions. We have some time for questions. So anybody here has a question, you could either raise your hand or maybe you could just unmute yourself and speak up also directly. That should also be fine. If more than one person speaks up at a time, then I can try and stop one of you. So while we are waiting for questions, maybe I can start with a short question which I had at one point. So you mentioned that Frege is not automatable unless cryptography breaks, and this is also an implication in only one direction. Are there any, for any system, not just extended Frege, but for any system, are there characterization results? It's automatable if and only if.
Yeah. Okay. So it is, in this case, it's, if it were automatable, then cryptography would break. And I don't think there is a reverse direction. So if it were automatable, then it would break. If it were not automatable, then, well, then you know that some problem is hard, but it's not a standard problem.
But it may not be the specific problem that you started with.
Certainly
right?
not a cryptographic one.
So this is for extended Frege, but maybe even for any other system. I mean, basically what I'm asking is, can this question of automatability be stated equivalent to something, some computational problem?
I mean, yeah, for resolution now we know yes.
Yes, exactly. Yeah.
Yes, your question is whether you can do it for stronger proof systems. There's been some line of work trying to extend our work, and so we managed to do it. These later works managed to do it for proof systems a little bit above resolution, like polynomial calculus and Sherali-Adams proof system. So for those, it's also NP hard. But other than that, I don't think there is a characterization of the kind you're looking for other proof systems. So
okay. Okay. Yes, I think, yeah, for cutting planes and Shirley Adams is.
For cutting planes, indeed. I forgot cutting planes.
Okay, yeah. Okay, any other questions? Okay, so I have one more question. So the soundness of the proof system resolution is not provable within resolution efficiently. What examples are there? Examples of systems where the soundness is easily provable within that system?
Oh yeah, absolutely. In their system itself. So one example is Frege. So Frege can prove its own soundness in polynomial size.
Frege, not even extended Frege.
You don't need extended Frege. Yeah.
Okay.
This is a result of some bus. Yeah, it relies on the fact that the Boolean. So what is it? The formula evaluation problem is in NC1.
It has efficient formulas.
Yes, and that's used in the proof. Yeah.
Okay. Yeah. So it has some kind of a self-referential flavor to it, and so it reminded me of your starting slide, Gödel and Neumann talking to each other.
Yeah, there's a big difference in that. In this case, consistency. So Sam Bass also showed that not only soundness is provable in Frege with polynomial size proof, but also the consistency. So these are bounded consistency statements. So you want to say, is there a proof of contradiction from nothing of certain size? And then you can refute this statement in polynomial size in Frege itself.
Okay.
So this is goes a little bit against Gödel's theorem. Gödel's theorem says that the consistency cannot be proved within the system itself, while for Frege it can. Of course, it's a bounded consistency. It's not general consistency.
Okay, so I still don't see any other. I hope I'm seeing the right. Yeah, I don't see any questions in the chat or in the. So I'll just wait for half a minute. If there are any more questions, speak up quickly now. So maybe I'm just open-ended. So what is the next big question here now in this? You mentioned feeding this to, getting the solving community in that, but that is not a proof theoretic question, right? That's a implementation.
Yeah. So now the big question in automatability is whether there is a proof system that simulates resolution and that is automatable.
And that is automatable. Okay.
So whether resolution is weakly automatable in the definition that we saw in the talk. So that's open, and that would completely close the question, because then no proof system at all. I mean, if you could show that it's not weakly automatable under some assumption, then there is no proof system that is automatable, right, above resolution. So,
but do you expect that it is weakly automatable?
I don't know what to believe. I thought that it cannot be weakly automatable, but I don't know. I change my mind from time to time.
Okay.
So, for example, tree-like resolution. That's another question. Can you weakly automate it in polynomial size, polynomial time, instead of quasi-polynomial time? That's not known.
Yeah, that's a very interesting question. Okay, so I think there's no more comments or questions coming up now. So everybody join me in thanking Albert once again for this very nice talk.
Thank you.
And so we close this session now, and those who would like to discuss further could head over to GatherTown if you like. Yeah.
All right. Thank you.
Thank you very much. Yeah.